Ladies and gentlemen, what if the biggest breakthrough in artificial intelligence wasn't building the world's most powerful supercomputer, but knowing exactly when to walk away from it? What if a project that shocked the tech world wasn't killed because it failed, but because it worked too well and revealed a smarter path forward? Today we are pulling back the curtain on a decision that reshaped the future of autonomy, redefined how intelligence is trained at scale, and proved that true innovation isn't about holding on to the biggest machine in the room, but about moving faster than anyone else when the rules change. Stay with me because this story changes everything you think you know about how the future is actually built. And behind the scenes of advanced AI development, decisions are rarely driven by emotion or headlines. They are driven by scale, efficiency, and long-term impact. The decision to step away from the DOJO supercomputer was not a retreat from ambition, but a calculated evolution in how artificial intelligence is built, trained, and deployed at a global level. What appeared to many as the end of a bold project was in reality a strategic pivot rooted in first principles thinking. And DOJO was created to solve a very specific challenge: processing massive volumes of real-world video data to train vision-based neural networks. At the time of its conception, existing hardware solutions were not optimized for this task at the required scale. Building an in-house supercomputer made sense because it promised tighter integration between hardware and software, faster iteration cycles, and control over a critical part of the AI pipeline. Early results proved that the architecture worked, and it successfully demonstrated that custom silicon could rival, and in some cases outperform, conventional solutions. And however, technology ecosystems do not stand still. While DOJO was being developed, the external AI hardware landscape advanced at an unprecedented pace. Off-the-shelf accelerators became more powerful, more energy efficient, and more cost-effective, while also benefiting from massive developer ecosystems and rapid manufacturing cycles. At the same time, cloud-scale infrastructure began offering flexibility that fixed proprietary systems could not easily match. The gap between custom hardware advantages and commercially available solutions narrowed faster than expected. And another critical factor was opportunity cost. Every engineering hour invested in maintaining and scaling a proprietary supercomputer is an hour not spent refining algorithms, improving data labeling, optimizing neural network architectures, or accelerating real-world deployment. As autonomy systems matured, it became increasingly clear that software improvements and data quality were delivering larger performance gains than raw compute alone. Redirecting focus toward these high-leverage areas aligned better with the company's mission of rapid real-world impact. And scalability also played a decisive role. Training advanced AI models is not a one-time event. It is a continuous process that must grow alongside expanding data sets. Scaling a custom supercomputer requires long lead times, specialized manufacturing, and significant capital expenditure. In contrast, leveraging a diversified mix of external compute resources allows for elastic scaling, faster upgrades, and reduced risk. This flexibility becomes especially valuable when AI workloads fluctuate or when new training paradigms emerge. And energy efficiency and sustainability considerations further influence the decision. Large-scale compute is energy-intensive, and optimizing performance per watt is just as important as raw throughput. External hardware providers compete aggressively on efficiency because their survival depends on it. By taking advantage of this competition, the company can access increasingly efficient compute without bearing the full burden of designing, validating, and cooling next-generation chips internally. And it is also important to understand that stepping away from DOJO does not mean abandoning custom innovation. The knowledge gained from designing the system fed directly into better software optimization, compiler design, and workload distribution strategies. Lessons learned from DOJO continue to shape how neural networks are trained and deployed, even if the hardware itself is no longer the centerpiece. And ultimately, this decision reflects a core philosophy: resources should flow toward whatever accelerates progress the fastest. When a tool no longer offers a decisive advantage, it is replaced regardless of how ambitious or groundbreaking it once seemed. This willingness to reassess and pivot is not a sign of failure, but a sign of discipline. And the broader implication is clear. The future of autonomy and artificial intelligence will be defined less by who builds the biggest supercomputer, and more by who can most effectively integrate data software and scalable infrastructure. By reallocating focus from proprietary compute to higher impact areas, the company positioned itself to move faster, adapt quicker, and deliver real-world AI improvements at a pace that fixed systems struggle to match. And this shift also revealed a deeper understanding of how modern AI systems evolve over time. As models grow more capable, the bottleneck is less about brute force computation and more about how intelligently that computation is applied. Training efficiency, data curation, and model architecture improvements began to outweigh the marginal benefits of adding more custom hardware. By focusing on smarter training loops and more adaptive learning strategies, meaningful gains could be achieved without continuously expanding a single monolithic system. And the autonomy stack in particular benefited from this refocused approach. Real-world driving data is noisy, diverse, and constantly changing. The ability to retrain models, quickly test them across varied environments, and deploy updates at scale requires a flexible compute backbone. Relying on a combination of external accelerators and modular infrastructure made it possible to iterate faster and respond more effectively to edge cases discovered in real-world use. This agility is difficult to achieve when locked into a single proprietary hardware roadmap. And there was also a strategic recognition that AI leadership is not solely defined by owning every layer of the stack. In some areas, vertical integration creates a strong advantage. In others, partnership and selective reliance on external ecosystems accelerate progress. By stepping back from DOJO as a primary pillar, the company avoided the risk of becoming overly attached to a solution that could limit adaptability in a rapidly shifting field. And another important consideration was talent allocation. World-class engineers are a finite resource. Maintaining a custom supercomputer requires deep expertise in chip design, low-level systems engineering, and hardware validation. While these skills are valuable, they are not always the highest impact use of talent when software breakthroughs are driving most performance gains. Redirecting engineering effort toward perception models, planning systems, and simulation environments produce compounding benefits across multiple products. And simulation and synthetic data generation also rose in importance during this transition. Instead of relying purely on raw compute to process ever-growing volumes of real footage, advanced simulation techniques allowed models to encounter rare and dangerous scenarios in controlled environments. These simulations could be scaled dynamically using flexible compute resources, reducing the need for a fixed in-house supercomputer, while still achieving robust training coverage. And financial discipline played a role as well. Building and scaling proprietary hardware at the cutting edge is capital-intensive, with long payback periods and uncertain returns. In contrast, leveraging competitive external compute markets converts large upfront investments into more predictable operational costs. This shift aligns better with long-term sustainability and allows capital to be deployed where it directly accelerates product improvements and manufacturing scale. And importantly, the move away from DOJO did not slow progress. In many respects, it accelerated it. Training cycles shortened, deployment pipelines became more resilient, and the AI stack gained the ability to adapt quickly as new hardware generations emerged. Rather than waiting years for a custom system to evolve, the company could immediately benefit from industry-wide advances in silicon and infrastructure. And this decision also sent a clear signal internally: no project is immune to reevaluation. Even highly ambitious initiatives must continuously justify their existence through measurable impact. This culture of accountability ensures that innovation remains aligned with outcomes, not sentiment or legacy commitments. And as AI systems continue to advance, the emphasis increasingly shifts toward holistic optimization. Hardware, software, data, and deployment must move in sync. Overinvesting in one layer at the expense of others can create imbalance and slow overall progress. By recalibrating priorities, the company reinforced a systems-level approach where every component serves a clearly defined purpose within the larger mission. And the story of DOJO, therefore, is less about cancellation and more about evolution. It represents a moment where learning surpassed necessity, where the experiment delivered its insights, and where the organization chose to act on those insights decisively. This adaptability remains a defining characteristic of how complex technological challenges are approached, ensuring that progress continues through constant refinement rather than rigid adherence to any single path. And this adaptability also reshaped how long-term AI roadmaps were defined. Instead of anchoring future capabilities to a single internal platform, planning shifted toward outcomes and performance milestones that could be achieved across multiple compute backends. This abstraction allowed teams to focus on what the system needed to learn and demonstrate rather than how the underlying hardware was built. As a result, research timelines became more resilient to external changes in technology and supply chains. And the data engine benefited significantly from this mindset. As fleets expanded and sensor fidelity improved, the volume and complexity of incoming data increased dramatically. Managing this flow efficiently required dynamic allocation of resources, intelligent filtering, and prioritization of the most valuable training signals. Flexible infrastructure made it possible to scale these processes up or down in near real time, ensuring that compute was always directed toward the highest impact tasks, rather than locked into static workloads. And cross-validation across different hardware environments also emerged as a quiet advantage. Training and testing models on diverse accelerators exposed subtle assumptions and inefficiencies that might otherwise go unnoticed. This led to more robust architectures that generalized better across conditions, improving reliability when deployed in the real world. The absence of dependence on a single custom system reduced the risk of hidden bottlenecks or blind spots embedded deep within the stack. And another shift occurred in how success was measured internally. Instead of celebrating peak theoretical performance or benchmark results tied to specific hardware, emphasis moved toward deployment metrics, real-world behavior, and rate of improvement over time. This grounded approach reinforced the idea that AI progress is only meaningful when it translates into safer, more capable systems operating at scale. Compute became a means, not a trophy. And manufacturing considerations also influenced this evolution. Building proprietary compute at scale introduces dependencies on fabrication cycles, yield rates, and specialized components. By decoupling AI progress from these constraints, development became less sensitive to manufacturing variability. This separation allowed hardware teams to focus on core product innovation, while AI teams continued advancing independently, each operating at their own optimal pace. And the competitive landscape further validated this strategy. As more organizations invested heavily in AI, the pace of external innovation accelerated. New architectures, training methods, and optimization techniques emerged rapidly. Maintaining flexibility ensured that promising advancements could be adopted quickly without being constrained by legacy design decisions. This openness to external progress reinforced a culture of continuous learning rather than insular development. And internally, collaboration improved as well. Teams working on perception planning, simulation, and infrastructure could iterate more freely without waiting for hardware-specific changes. Shared tools and standardized interfaces reduced friction, enabling faster experimentation and clearer feedback loops. This cohesion amplified the impact of incremental improvements, compounding gains across the entire system. And risk management was another understated benefit. Concentrating critical capabilities within a single proprietary platform introduces systemic risk. Any delay, defect, or performance shortfall can ripple across multiple programs. Diversifying compute strategies mitigated this exposure, creating redundancy and optionality. This resilience is particularly important in fields where rapid iteration and reliability are both non-negotiable. And the lessons learned extended beyond AI alone. They reinforced a broader organizational principle: innovation is not defined by how much is built internally, but by how effectively resources are aligned with mission-critical goals. Sometimes that means building from the ground up. Other times it means recognizing when the ecosystem has caught up and reallocating effort accordingly. And as training methodologies continued to evolve, emphasis shifted toward curriculum learning, self-supervised techniques, and continual learning from deployment feedback. These approaches rely less on sheer compute scale and more on intelligent system design. Flexible infrastructure supported these methods more naturally, allowing experimentation without committing to massive long-term hardware investments. And the legacy of the supercomputer effort remains embedded in the organization's DNA. It sharpened understanding of AI workloads, exposed inefficiencies in existing tools, and pushed teams to think holistically about performance. Even without serving as the central engine, its influence persists in optimized pipelines, smarter scheduling, and a deeper appreciation for the trade-offs involved in large-scale AI development. And this ongoing refinement reflects a commitment to progress over permanence. Systems are expected to evolve, assumptions are expected to be challenged, and strategies are expected to change as evidence accumulates. By embracing this dynamic approach, the company continues to advance complex AI systems with speed, discipline, and a clear focus on real-world impact rather than attachment to any single technological artifact. And this mindset continued to influence how future infrastructure decisions were evaluated. Instead of asking whether a system was impressive or unprecedented, the more important question became whether it measurably accelerated learning, deployment, and safety. Every component of the AI pipeline was examined through this lens, from data ingestion to model validation. If a tool no longer created clear leverage, it was either reworked or replaced regardless of the investment already made. And as real-world deployment expanded, feedback loops tightened. Models were no longer trained in isolation and judged months later. They were continuously refined based on live performance data. This demanded compute resources that could respond instantly to changing priorities. Flexible infrastructure allowed training jobs to be reshaped around new insights, whether that meant emphasizing rare edge cases, adjusting perception thresholds, or refining long-horizon planning behavior. Static systems struggled to keep pace with this cadence. And the evolution also changed how experimentation was conducted. Smaller, faster iterations replaced fewer massive training runs. Instead of betting everything on a single large-scale job, teams could explore multiple hypotheses in parallel, compare outcomes quickly, and discard unproductive paths early. This approach reduced risk while increasing overall learning velocity. It favored adaptability over raw scale, reinforcing the shift away from dependence on any single compute solution. And another subtle but important effect was the democratization of progress within the organization. When compute access is flexible and scalable, more teams can experiment without competing for limited internal resources. This broadened participation in innovation, allowing insights to emerge from unexpected places. Improvements in perception, prediction, and control often came from these decentralized efforts, compounding gains across the system. And the autonomy challenge itself continued to underscore why this flexibility mattered. Driving is an open-world problem with virtually infinite variability. No fixed dataset or one-time training approach can capture its full complexity. Continuous learning from diverse conditions is essential, and that learning must be supported by infrastructure that can evolve alongside the problem. By avoiding rigid commitments, the AI stack remained aligned with the unpredictable nature of real-world environments. And this approach also strengthened validation and safety processes. Running models across diverse hardware and infrastructure configurations exposed inconsistencies and corner cases earlier. It encouraged more rigorous testing stress scenarios and cross-checks, reducing the likelihood of hidden dependencies. Safety improved not because of more compute alone, but because systems were designed to be examined from multiple angles. And economic efficiency remained an ongoing consideration. As AI workloads scaled, cost control became inseparable from technical performance. Efficient use of external resources combined with smarter scheduling and workload optimization ensured that growth remained sustainable. This balance between ambition and discipline enabled long-term investment in AI without compromising broader operational goals. And over time, the distinction between research and production blurred. Models moved from experimentation to deployment faster, and lessons from deployment fed directly back into training. This continuous cycle demanded infrastructure that could support rapid transitions without friction. The decision to move beyond a single centralized supercomputer made this integration smoother and more resilient. And culturally, this reinforced an engineering ethos centered on outcomes. Success was defined by real-world capability, reliability, and rate of improvement, not by attachment to any specific project. Teams became more comfortable letting go of past solutions when better paths emerged. This openness reduced internal inertia and kept innovation aligned with evidence rather than tradition. And the broader AI industry continued to evolve at high speed, validating the importance of this stance. New training paradigms, hardware architectures, and optimization techniques emerged regularly. By maintaining flexibility, the organization could adopt what worked, ignore what did not, and integrate advances without disruption. This selective adoption proved more powerful than attempting to lead every layer simultaneously. And ultimately, the progression away from a singular compute centerpiece reflected a mature understanding of complexity. Building intelligent systems at scale requires constant recalibration. Tools are evaluated, lessons are absorbed, and strategies are refined in response to real data. What mattered most was not preserving a particular system, but preserving momentum. And this ongoing process ensured that AI development remained grounded in practicality while still driven by bold goals. Each iteration sharpened focus, reduced waste, and increased impact. The emphasis stayed firmly on building systems that learn faster, adapt better, and perform more reliably in the real world, guided by a willingness to evolve whenever evidence demanded a change in direction.